Uh, Now we are in this video we are in the chapter 11 in the BSL, but before just going on the chapter 11, I just want to just remind and review the conservation of linear momentum for continuum case. Before we draw this equation, actually for the linear momentum, we know this is the stress forces acting on the fluid because of the external forces like pressure and the viscous forces and these body forces. After that, we can define the external forces like a total stress tensor by these terms. In here, these viscous forces, and this is the P is the pressure. Then we can insert here so we can obtain this equation. We have at the left side is the substantial derivative. We know the we have the in the BSL actually the open form of this equation. And so anyway, we have seen this before in the previous videos. So let's continue. Now we are in here, mechanical energy balance. Uh, by taking the equation of the momentum, if we take the dot product between the equation of motion and the vector, velocity vector, then we can obtain mechanical energy balance. So dot product at the left side and dot product between total stress between this term and that one, and body force and that. And here now we can define this term again, the equivalence like this. This is going to be equal, that one is the trace. We have seen the meaning of the trace in rectangular element, summation of rectangular element, and not a summation of the element in the matrix this form. So we can write this term by this two term here in here. Finally, if we take this term instead of that one, we can insert here, and at the left side we obtain, you see, 1 over 2 v square is, we call this the kinetic energy term, is we call this total under accumulation rate of the mechanical energy. We know for the mechanical energy term. In here we have the rate of work done this by the stress vector uh, on the fluid, and in here we have the rate of the conversion of mechanical to thermal energy. That term is represent that one, and this is the rate of work done by the body forces, and we have this, we call this the mechanical energy balance. In the next part, we just go for the conservation of the total energy. We just divided in here the energy by three form. The first one we call mechanical energy equation, and second we are gonna define in here total energy equation, and in here we define another energy term is we call the thermal energy equation. In here the thermal energy equation is the total energy equation minus mechanical energy equation. This is going to give the thermal energy equation from here actually. So in this slide we're just gonna touch the derivation of the total energy, conservation of total energy, and the terms in the total energy equation. The body mass process energy is internal energy. We define, we know from internal energy. Any control system inside of the body, it's contain some type of energy. We call this the internal energy, and this shows per mass. And we know it has also the kinetic energy we draw for in the mechanical energy equation. Also another term we define like in chapter 9 in BSL, heat flux due to the uh, molecular transportation of the energy. and another one is we call the radiation term. These are the rate per mass. Heat transfer is due to the temperature difference. So energy transfer by work due to the external forces, like we define the work term before. The work is the any body, and on the body F is forces acting and taking this body from some x1 to x2, and we call this dr, and finally we obtain this work term from here. So the total energy is conserved, no generation or no consumption, and so conservation of total energy for material volume can be written like this at the left side. At the left side, we can write internal energy and mechanical energy. In here, we just write the heat flux term, and in here, radiation term. In here, forces, external forces term, and in here, uh, some another we defined before. It's come from like gravity and other forces. So we can write this that one same here, like we can write this from the divergence theorem in this form. This is going to be same. We can convert this again to this term by using the divergence theorem. This is going to be same by going in the next slide. So we can write finally the total energy conservation, the rate of accumulation of the energy inside of the body and control system, internal energy plus kinetic energy, and heat energy transport by conduction, by radiation, and total stress acting on body, and those external forces because like gravity or so on. So now we can write the thermal energy, as I say before, total energy term minus uh, uh, mechanical energy term. If you remember, this is our actually mechanical energy term here we draw before. Now, if we come here, if we come here, uh, anyway, so if you come here, subtracting from the mechanical energy term from the total energy term, we obtain from here. So in mechanical energy, we had like kinetic energy, and there's it is going to be minus. This is going to this is uh, positive. So these are cancel each other. Okay. Now we just get uh, from okay. Okay, we don't have this term in the mechanical energy, and this term is going to come here. We don't have that one in mechanical energy. This is going to come here, and these are the same signs. And at other one, we have we have we have actually these two terms. You can write here, and these two terms from here, they are going to cancel each other, and we just take these terms. This is going to be minus, this is going to be plus, actually should be plus. Oh, no, this is not the plus, just we have just these two terms. Okay, so on. So these are going to cancel each other, and we are just going to keep that one. This is going to be plus, and this is going to be pressure term is going to be minus. So why this minus? Okay, anyway, so this is our thermal energy balance. This is the input rate due to the conduction, input rate due to the radiation, and this irreversible conversion rate of mechanical to thermal due to the friction. And this is going to be the reversible conversion between the mechanical and the thermal energy due to the expansion or compression. So in here. So actually just we review our derivation of the our total energy and mechanical energy and thermal energy. So now we can move on the chapter 11. If we go and chapter 11, uh, basically for the derivation of the total energy, what we obtain at the left side rate of increase of the kinetic and internal energy, summation of these two terms. As the first term, we obtain net rate of kinetic and internal energy addition by convective terms transport. In the slides, we just put this term inside of substantial derivative. Another term, net rate of heat addition by molecular transport, but the other mean is conduction. Another one, rate of work done on system by molecular mechanism like stresses and total stresses. And the final one, the rate of work done on the system by external forces like gravity. In here, we don't consider radiation in the book. So, okay, when we just go, okay, this uh, we know from the chapter 9. In the chapter 9, we just obtain this E term. What was this E term? We call this in the chapter 9 the combined energy flux vector, and the first term was the convective term in the transportation of the energy by convection. The second term was this term, uh, forces acting on body like total stress term, and this term Q is going to be here energy transport by molecular transport by conduction. This is the in terms of U, internal energy. If we define this total stress in chapter 9, this symbols can be changed, but they has the same meaning. And we can write here the pressure plus viscous forces again. Finally, we can define this term, internal energy include term plus pressure term, is give us the definition of the enthalpy. So then finally, we can write this relation. In here, we have total stress, but in here just viscous stress. We just dump the pressure term inside of the enthalpy. So this is going to be another form of this um, total combined energy flux. So now you are taking this E total energy flux and we put inside of the total energy equation at the left side rate of accumulation because of the kinetic energy and U. In here we have total combined energy flux. At the right side, this final term is going to be external forces on the energy term. And we can write this term by E. It's like this. And what's going to be the open form of this equation? We keep just the same, and we can write this. First one is the combined three terms, actually, this E again here. This is combined. One is convective. Number two is molecular, like conduction. Number three is going to be forces because of due to the forces, energy transfer due to the force like viscous forces and pressure and so on. So now we can write, you see the first term here is going to belong the convective term inside of this E. The second term is going to be Q, conduction by the molecular transport. All of this is the per unit volume. This is going to be, this 2 is going to be uh, total stress, big T, but we can write it by two terms. This is summation of these two terms. The first one is going to be rate of work done on the fluid per unit volume by pressure forces on the fluid. Second one, viscous forces. And finally, we have here the external forces, rate of work done on the fluid by external forces, so on. So this is our total energy equations, different than our slide here because we have here this substantial derivative, but this time this book is not considered substantial derivative in here. anyway. In here, we can define inside of the external forces G can be defined like this term. This term is represent just potential energy per unit mass, and we can write this gravity multiplied by h. H is going to be any coordinate in the direction opposite the gravitational field. Now we can write this term by inserting this term inside of this term. We can obtain this final one, and partial derivative, the time change of this potential energy is going to be zero. That's why we can have that term obtained here. And now we can write, instead of this term, we can write that term here, and we can just take sorry, this is not zero. We can take this side to put here in the left side. We can put this in here in the convective term, and we can write this total energy equation by another form of this. So we can represent the energy equation and mass transfer equations by different various forms. All of them same, nothing changed. You can write in terms of U, in terms of enthalpy, in terms of potential energy, and in terms of the external force, so on. Okay, so spatial form of the energy equation, we know this from before. This is our mechanical energy equation we obtained before. The left side, rate of increase in internal energy per unit volume. Oh, sorry, this is the yeah, internal this this is going to be our sorry, not internal mechanical energy. This is going to be our thermal energy. What we are doing here, we are just taking the total energy equation minus mechanical energy equation is going to give this thermal energy equation. In here, the first term is represent rate of increase, the internal energy or change per unit volume. The first term, net rate of addition of the internal energy by convection transport per unit volume. We can, when we take this term put here, we can write this substantial form. This is again our heat conduction term, and this is reversible rate of internal energy increase per unit volume by compression because of the pressure forces acting on fluids. And this is going to be our irreversible rate of internal energy increase per unit volume by viscous dissipation term. We know where this terms comes from, actually from the other videos and other slides. So okay, let's continue. This is the spatial form of thermal energy. Now we have this thermal energy, but we can write this thermal energy by this form, as I said before. We can dump this convective term in the left side, and we can write this as a substantial derivative again. At the same times, again, we can define the U as enthalpy minus PV, and we can write this enthalpy P over rho, and we can write this by in terms of uh, this term by enthalpy, and this is going to be same by this equation, and this substantial derivative of the enthalpy respect to T, and we obtain it in here another term is dP over dt. We know from the chapter 9 we can write the enthalpy change respect to time by this formula, and now finally we can get that one, and we can just insert here. When we insert here, this is going to be the first term is going to be here at the first left term, and we just take this all, we can write here instead of, we can insert here, and this is going to be keep here, but we just take this at the right side. That's why it's minus sinus comes from. We had that one before, and we have also that one here. This is going to be minus, and this is going to be minus. They are going to cancel each other. Finally, we are just going to just keep that term in here. This is the equation of change for temperature, actually, in terms of the heat flux vector Q and the viscous momentum flux, that one, we know this viscous momentum. To use this equation, we need to expression for these fluxes. We need to open this. Okay, we know from the chapter 9 our conductive flux is going to be equal that one. For a special case, if the K conductivity of the species if constant, then we can write by this form actually. Then we have this term here, viscous forces term. We can write this by this form, like here. This is the form, the dissipation flux actually. Okay, but in we can just get some assumption and we can simplify this equation. For example, for the ideal gas, this term is going to be -1, that one, and we obtain that one. And for the ideal gas, we just ignore also this term, term here. This is the first special case we can write. Or we can just, in here we obtain this equation in terms of Cp, but we can obtain this equation also in terms of Cv, and we have another term is going to be keep here. Another special case for the fluid flowing in the constant pressure system, then dp over dt is going to be 0. Then we will have that form. For the fluid with constant density, then this term is going to be 0 in here. Again, we will have that term when just ignoring that effect of that term also. And finally, we can write for the stationary solid, v is going to be 0 velocity vector, and this is basically going to be get this form actually for the spatial case. Okay, now we can go and check some section 11.4. In section 11.4, similar manner in the momentum transport. In this, just show the steps for the problem solution. If you just encounter any problem, first you need to go check the for the problem the equation of continuity, and then the equation of motion for the containing mu and viscosity and the k, another viscosity term. Then the equation of energy containing viscosity, another viscosity type of viscosity, and k is the conductivity. And thermal equation of the states, P, pressure is dependent on the rho and T, and your caloric Cp depending on your rho and T. Now, let's in here in chapter 11, table 11.41 is gives us different forms of energy equation and other equation. The first one is the, you see from here, the equation of continuity for the constant rho. Just this term is going to be 0 and this is going to be 0. And equation of motion, we obtain that form uh, for the viscous forces equal, if it equals to 0, then becomes Euler equation. Okay, energy form in terms of kinetic energy, internal energy, and potential energy, we can write by this form. In terms of kinetic and internal energy, then we will have another term here, pressure term, another term. Okay, yeah, external. Okay, sorry, not the pressure, external term. But another form in terms of the kinetic energy, we can write this form from the equation of motion. This is the mechanical energy equation. In terms of U, thermal energy equation is going to be this. In terms of energy, we can write this instead of the U, we can write by the enthalpy. It's going to be this equation. So basically, for the problem solution, you can utilize this equation because they are already here, and you just need to take them and simplify and just adapt your problem solution. You can write this in terms of CV constant volume heat capacity and or CP, constant pressure heat capacity, and so on. You can check all these tables. Okay, now let us go this example 11.41. In here is talking again the steady state forces convection heat transfer in laminar flow in circular tube. We have seen this before actually. We in the momentum transport. It was one of the example if you remember. Okay, let's go the problem statement. Let's consider again we have a circular tube like this. Okay, this is going to be z is equal 0. This is going to be z is equal L, and this is going to be center of your tube, and this is going to be R radius of your tube. From here, all the properties, viscosity, conductivity, density, and Cp is assumed constant, all of them constant, and we can consider this laminar flow. For the z less than 0, that means before enter the tube, the fluid temperature is defined as a T1. Okay, fluid is coming from here and then enter, but before enter the tube, the fluid temperature is T1. For z is greater than 0, there is going to be some radial heat flux from the tube wall. You see, when you see this wall is going to be has some source which just provides constant QR, and this we show Q0 from the wall. This minus because we obtain from outside to inside. So if we just give the heat from inside to outside, this is going to be plus sign conversion. So, okay, anyway, in here uh, it's called this uniform heating in everywhere. So this problem asking, okay, just derive the necessary conservation equation to solve the temperature profile. So if you remember before, we solved this for the velocity profile. You obtain just parabolic velocity distribution. Our Vz was going to function of the r before we obtained that one. Now this is asking the temperature as a function of z and r here. So okay, let's go check again here. In here we know from the before, in here because we are in the cylindrical coordinate, vr was 0 and v theta was 0 before. We know this knowledge from before. Okay, uh, let's continue our discussion. First of all, for this problem, let's check some our equation of continuity for that one. Uh, Sorry, let's check again. Okay, our equation of continuities you can go and find in the table appendix B. Equation of continuity for this problem, we are in just here in the cylindrical coordinates. Since our rho is constant, that's why this term is going to be 0. Since our Vr and V theta is 0, this term is going to be 0, this term is going to be 0. Finally, we obtain that once the rho is constant, we can take this out of partial derivative. We can write this dvz over dz is going to be 0. From the equation of continuity, what we see, the intro the tube, circular tube, velocity distribution is not dependent on the z direction, just dependent on the r direction. So this confirm that velocity distribution, this result comes from the equation of continuity. So This is our first steps for the first step for the problem solution. And let's go in second step. In the second step, we need to go check equation of motion actually. Okay. Now again go in the table appendix B, equation of the motion, like in terms of the viscous forces. Again, we are in cylindrical coordinate in here. This is just our coordinate. This is going to be 0. We are 0, 0, 0, 0, and v theta is 0. And this is going to be 0. This is going to be 0, and this is going to be 0. This is also going to be 0 since dz was 0. From here we can write 0, and finally we obtain that one. The left side is 0, right side is going to be, as we defined before, minus pressure, partial pressure, dr plus rho dr. So we can define this, that one. We can just write p plus rho gr is just big P, new variable. Then finally we can obtain this is minus dp over dr. Okay, it's for our direction. For theta, it's going to be 0. It's going to be 0, 0, 0, 0. At the right side, it's going to be 0. It's going to be 0, 0, and 0. Finally, we have similar. Left side is 0. dp over 1 over r d theta. For the z direction, uh, for the z direction is going to be 0. It's not dependent time steady state. We are 0, we theta 0. From here, dz is 0. From here, this is going to be 0, this is going to be 0. And finally, what we have on the left side was going to be 0. At the right side, we have obtained partial derivative of pressure respect to z and minus 1 over r partial derivative of r viscous force in the z direction perpendicular to r direction plus rho dz, and we can just write in the new type dp over dz, and this is also going to be minus 1 over r r. We can write this minus mu is constant, so we can write this minus mu uh, dvz over dr, and we can take this out, and this is going to be plus, and we can take also this mu outside is constant. We can write this in this form like this. Okay, this is our equation of motion. You remember from the actually chapter 4. In the chapter 4, we obtain the solution of this problem. If you remember, let me show again the solution of this problem in chapter um, 4 in the momentum transport. In here, actually, if you remember from in chapter 4, sorry, in chapter 3, sorry, not the chapter 4. Chapter 4 was about the velocity dependency for the more than one variable. In the chapter 3 and the problem solution part, okay, stay flow in the long circular tube. As we've seen, we just obtained similar things, and we obtained this finally. And the solution for this equation for the boundary condition was that one. That one was our actually velocity distribution through the circular tube. We obtained that one. Now we can continue our discussion here. Okay, for this problem. So where we are, we just obtain the continuity equation. Just obtain the equation of motion. We know the solution of this um, uh, equation. From here, we just when we obtain the Vz term, and we can insert here, and we can find the energy equation. But first, let's go check and how we obtain this energy equations comes from. Okay. In the similar manner, if we go to appendix B for the table for the energy, for the heat flux in the cylindrical coordinate can be represented by these formulas. For the equation of energy for pure Newtonian fluid with the constant rho and the k, this is the just expressed in our problem. In our problem, our viscosity, rho, and k are constant. Then this is our general equation. We know from that. And this is the conductivity term. And this is the dissipation, basically dissipation function. And this is the open. This is the this we go again in here. Uh, this is just open form of in the thermal energy equation, that one. Okay, let's just show that one is viscous forces. Viscous forces in here can be represented by that one dissipation function here. These are going to be same here. Okay, let's continue our discussion in energy equation. Okay, we are now in cylindrical coordinates. Cylindrical coordinates. Since we are in steady state situation, then this is going to be zero in time, and our VR and V theta is zero. That's why this term is zero. This term is going to be zero. Finally, from here we just obtain rho and Cp per mass, constant pressure heat capacity. We z, this is not constant, we obtain from the equation of motion, and the t over partial derivative of t respect c. At the right side, uh, at the right side, actually, at the right side, as we mentioned in the problem, temperature is just function of the z and r. That's why this term is going to be zero, and we will have that term from here just left, 1 over r partial derivative of uh, r dt over dr. We know this two term is just the form of conductivity, molecular transport of energy, and from here finally we left here this term. This function is given in the table B.7. To find this function, let's move on the table 7. From here, the table 7 I just take here is our table 7. For the dissipation function, we are in cylindrical coordinates. Okay, to find the dissipation function from here. Okay, this term is going to be zero because we are zero, Vt is zero. Okay, the change of the Vz respect to z is zero. We obtain from the equation of continuity. If you remember, this is going to be zero, zero, and this is going to be zero, zero. This term is zero, zero, and this is zero. And we have on this zero, we only get as a final, this dissipation function is going to be equal the Vz over Vr square. Okay, when we take this term from here, just when we insert here, finally we obtain the form of the equation exactly here. You see from here. Then we already solved that one, and finally we can solve that one for the boundary condition. Okay, finally you see for the problem solution to solve this equation. What should we do? Actually, we solve from this what is Vz, and we just take this solution, insert here. Finally, we can get assumption. The first assumption is in the z direction, heat conduction is much smaller than the heat convection, so that this term here can be neglected, can be assumed like a close to zero. And as the second one, the flow is not sufficiently fast that viscous heating is significant. Hence, the term in this term can be also omitted here, can be assumed like a zero. Finally, what we'll have, we will just have this two term here actually. So then we can solve this problem by this assumption. So what we have seen this problem for any circular tube, we just define our problem. We just define our assumption. Our assumption mu, rho, k, and all of them was constant, and we assume this steady state problem. For this, as a first step, we define our continuity equations. As a second step, we define our equation of motion, and then we define for equation of motion for our boundary condition and solve this equation by Vz. We obtain from here Vz, velocity distribution of the Vz, and that's what's function of the R we just obtained. As a third step, we just go find the energy equation for this problem. We obtain this final form, and we also apply some extra assumption, like this term, a conduction in the z direction much smaller, and this term is distribution function is small respect. Then later we just left these two terms, and then finally we can write some boundary condition, and we can solve this problem, some mathematical methods as we discussed before. Okay, now basically this is our goal here in the chapter 11. Just show total energy equations, mechanical energy equation, total minus energy equation minus mechanical energy equations give thermal energy equations, and finally show different forms of this energy equation in the table. And now then just give some example of this example 11 for 1, and go appendix B, show how to use the continuity equation, how to simplify them, finally how to solve any energy problem step by step. Okay, this is the end of the this video and chapter 11 actually. Now later, in the later videos, after finishing all the chapters, we will come back and discuss the more detail in the problems. But now I will just go and jump into chapter 12 and discuss some problems in temperature dependency with more than one independent variable. And later, I'm just gonna go interface transport in non-isothermal system, and I'm just gonna finish this part energy transport, and move the mass transport part in the later videos. Okay, so see you in the next video.